an interesting problem there, namely that when you do a horrible calculation and the answer comes out extremely simple, that tells you there's some hidden structure. But I've hopefully also convinced you that developing these new methods is actually of practical value for the community. So now let me, I feel like I've said as many words as someone of my juniority should be permitted to in a talk, so now let me focus on some equations. And basically, a large percentage, I don't want to estimate, but a large percentage of insights into scattering amplitudes of massless vector particles can be made just by understanding the right variables to express things in terms of. Okay, it may seem like a dumb comment, but really it's impossible to understate or underemphasize its importance. So in textbooks, you're typically taught to think of a scattering amplitude for a vector particle as a function of the 4 momentum k mu and a polarization vector epsilon mu for each particle. For each particle, you will have, let's say, 8 pieces of data, 4 components of k and 4 components of epsilon. Of course, there's a huge redundancy in this amount of data. First of all, because for a massless on-shell particle, k always has to be a null vector. Secondly, gauge invariance implies that epsilon and k should always be orthogonal to each other. And moreover, the choice of epsilon is ambiguous or irrelevant. Gauge invariance implies that any epsilon is as good as if you were to take epsilon plus any constant times the 4 momentum k. So there's a huge redundancy in this choice of variables. Spinor helicity variables package this information much more compactly. So the basic idea is really simple. You take your 4-component null vector and you decompose it using the Pauli matrices. So sigma mu are 4 2x2 matrices. That is, the 0 component here would be the identity matrix, and the other 3 are the Pauli matrices. Lambda and lambda bar are lambda is a complex 2-component spinor, and lambda bar is its complex conjugate. And the fact that you've written the 2x2 matrix in this way guarantees that it has determinant 0, and that translates into the fact that this k is null. So this is a way of, if you will, solving the constraint k squared equals 0. And also there's a formula you can write down, which I won't do so here, that lets you express the polarization tensors in terms of lambda and lambda bar. And then the notation that I used on a couple slides ago when I introduced the 5-particle amplitude, use this bracket notation where I and j is just the inner product of the spinors corresponding to 2 different particles. So more generalizing the result that I showed you before for 5 particles, it turns out that if you have any number of positive helicity particles, but only 2 negative helicity particles, this is what we call an MHV, or maximally helicity violating amplitude. And the answer is given by this stunningly simple formula. And it turns out that next to MHV and next to MHV formulas get progressively more complicated. And I should emphasize that, for example, until 2005, there was no known NMHV formula in the literature anywhere, because the calculation of such an object would have just been prohibitively difficult. Now, of course, with modern technology, you can literally write down the answer. I mean, you can literally write it down from memory or derive it on the back of an envelope with no problem. So Witten wrote a very influential paper in 2003 which sought to explain this simplicity. I won't go into too many details here. He was motivated by an observation due to Nair that you could write the MHV amplitude essentially as a free fermion correlation function. I'm suppressing a couple of irrelevant details here. But importantly, you know that a scattering amplitude always has an overall factor of energy momentum conservation. That's reflected in this delta 4 here, which I've chosen to write as an exponential. in that way. Of course, I'm setting 2 pi equals to 1 in this talk. And now, you know, when I don't know about you, but when I see d4x, I think, okay, it's time for me to load up Mathematica. But when Witten sees d4x, he says, aha, that is the measure on the moduli space of lines in P3. And that's one of the many differences between me and Witten. So Witten said, well, gee, if MHV amplitudes are supported on lines in P3, which is a fancy mathematical way of saying twistor space, perhaps next to MHV amplitudes will be supported on quadratic curves, and next to MHV amplitudes will be supported on cubic curves, etc. So the twistor string, so let me say a little bit about twistor space P3. Here's the idea. Start at the bottom of this slide and observe, recall this is the relation between momentum and lambda here, which I forgot to bar. This has only a very mild redundancy left over. And that is if you scale lambda by any complex number and scale lambda tilde by its inverse, then k remains unchanged. So it's convenient to do what we call a Fourier Penrose transform, a poor man's version of Penrose transform, or essentially just a Fourier transform, where you transform lambda tilde or lambda bar to a new variable called mu. And then the Fourier transform variable mu transforms oppositely to lambda bar. That is, it transforms the same way as lambda. So now you have 2 lambda variables and 2 mu variables. And your amplitude should be unchanged if you rescale all 4 of those by the same complex number. And that's the definition of what mathematicians call P3. So Witten's conjecture is that if you have any scattering amplitude with k negative and n minus k positive helicity gluons, it should vanish unless all n points lie on a curve of degree k minus 1 in P3. That is, the z's must satisfy some polynomial equation of degree k minus 1. So I'm continuing my, this was sort of the genesis for a lot of recent interest amongst the community for looking at scattering amplitudes and taking this problem seriously. Of course, given the fact that this is a cruising altitude talk, I don't have a chance to go into every